Hello there, and welcome to the Sleepy Science Channel. Tonight, we begin with a simple but unsettling thought. What if the world around us is not what it seems? Through the ages, and in many ancient traditions, people have wondered if reality might be a kind of dream. For most of history, those ideas were treated as philosophy or myth. But today, modern science has begun to ask the same questions, armed with mathematics, quantum theory, and the extraordinary rise of computation. Perhaps the ancients were right. And perhaps the Matrix is more real than you might think. We find ourselves asking, are space and time fundamental, or are they made of invisible lines of code? Is matter real? Or is it just information being processed by an unseen machine? If you enjoy these gentle journeys, I invite you to like and subscribe. Or share your thoughts down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, get relaxed and allow your mind to settle into this strange idea. Tonight, we'll explore the fascinating science of simulation theory. For centuries, the picture of reality was one of order, solidity, and predictability. Newtonian physics described the world in terms of elegant laws that governed every motion, from an apple falling to Earth to the planets circling the sun. The metaphor of a great clockwork machine captured the spirit of the age. If one knew the initial conditions and the forces at play, then the future of any system could, in principle, be calculated with certainty. Things made from matter were thought of as fundamentally solid. A stone in the hand seemed firm and unyielding, and the ground beneath our feet felt immovable. Light was pictured as a wave traveling through an unseen medium. Space was infinite and absolute, and time flowed evenly everywhere. The universe was conceived as continuous, mechanical, and eternal. It was a comforting vision of permanence, one in which nature could be trusted to follow rules that were stable across all of space and all of time. Yet the progress of science began to peel back the surface. As physicists explored the inner workings of the atom and the structure of light, the firm foundations of Newton's reality began to dissolve. At the beginning of the 20th century, quantum mechanics shattered the old assumptions. What seemed solid revealed itself to be mostly emptiness, with electrons circling nuclei like ghosts in vast spaces. But even the orbiting electron model quickly proved misleading. Electrons did not move like planets around the sun. Instead, they existed as clouds of probability, mathematical wave functions that described where they might be found if measured. A particle could occupy many possible states at once, a phenomenon called superposition. It could be here and there, moving and still, until some interaction forced it into one outcome. This was not just theory. Experiments confirmed that particles interfered with themselves as if they were in many places at once, only collapsing into a definite state when observed. Superposition was unsettling enough, but tunneling added further strangeness. Particles could slip through barriers as though the walls of reality were permeable. Entanglement deepened the mystery still further. Two particles born together remained linked across any distance. Their fates correlated in ways that defied classical explanation. Measure one, and the other responded instantly, as if information traveled faster than light. Quantum mechanics was mathematically precise and technologically indispensable, yet it painted a reality woven of uncertainty and potential rather than solidity and certainty. This raised the haunting question of measurement. If a quantum system existed in many states at once, what exactly caused it to select a single outcome? Did observation by a conscious mind collapse the wave function? Did the mere presence of a detector count? Or did the environment itself act as the observer, constantly nudging probabilities into concrete events? This was the measurement problem, a puzzle that continues to divide physicists. Some interpretations propose that wave functions truly collapse, while others argue that all outcomes occur, spawning countless parallel universes. Still others claim that probabilities are fundamental and no deeper reality lies beneath them. The strange thing was that quantum mechanics worked flawlessly as a predictive tool, while offering no single agreed picture of what reality actually was. It became clear that observation was not a passive act, but an event that participated in shaping what was real. Reality seemed to require interaction to crystallize into form, as though it remained a haze of possibilities until touched by the act of being measured. The clear boundaries that classical physics had promised dissolved into paradox, and the line between perception and reality blurred. As science pushed further into the very small, physicists encountered a new limit that challenged the idea of continuity itself. At scales near the Planck length, an unimaginably tiny distance, the smoothness of spacetime appeared to break down. Below this threshold, our familiar concepts of distance and duration lose their meaning. Try to slice space or time more finely, and the very act of measurement ceases to make sense. The Planck scale suggests that the universe is not infinitely divisible but quantized, pixelated, like the pixels of a digital screen. Energy fluctuations at these scales are so intense that space-time itself becomes turbulent, foamy, and uncertain. The Planck time, the shortest meaningful unit of duration, further emphasizes that time itself may come in indivisible steps rather than flowing continuously. Just as a high-resolution image appears smooth until magnified, space-time too may be fundamentally granular when examined deeply enough. Instead of an unbroken continuum, reality could be built upon a finite set of building blocks, indivisible units beyond which nothing smaller exists. This picture strips away the last illusion of permanence. Not even space and time themselves may be continuous. They might instead be constructed from discrete elements. These discoveries gave rise to a radical new vision: digital physics. In this perspective, the universe is not a smooth and independent fabric, but a vast computational structure. Matter, energy, and even space-time can be understood as information being processed. The laws of physics become algorithms, the particles of nature become bits of data, and the unfolding of the cosmos becomes a computation playing itself out across an unseen substrate. The speed of light may not just be a physical limit, but a maximum rate of information transfer. Entanglement may not be spooky action at a distance, but rather evidence of shared information in a hidden code. The granularity of space-time at the Planck scale begins to look like the resolution of a simulation. In this view, galaxies, stars, and life emerge not from solid substances, but from rules operating on information, the way complex patterns emerge in cellular automata or computer models. It is a worldview that unites physics with computation, suggesting that at the deepest level, reality is not matter but math, not substance but structure, not permanence but processing. From the clockwork order of Newton's world through the uncertainty of quantum mechanics, into the graininess of space-time and the idea of digital physics, our picture of reality has grown steadily more abstract. Each layer removes a little more of the solidity we once trusted, replacing it with something subtler and stranger. What once seemed like firm ground becomes fluid probability. What once seemed infinitely divisible becomes quantized into pixels. What once seemed substance may instead be code. The strange texture of reality hints that we are brushing against something profound, a hidden layer where physics and information theory converge. The suggestion is difficult to ignore. If the universe behaves like data, if its limits resemble those of computation, then perhaps what we call reality is already, in some sense, a simulation. The question is not only whether such a thing is possible, but whether science itself is beginning to reveal it. In the late 20th century, the physicist John Archibald Wheeler proposed a phrase that has since become iconic: "it from bit." What he meant was that every particle, every field of force, and even the very fabric of space-time ultimately derives its existence from yes or no choices, from binary information. Reality in this view is not constructed from continuous substance, but from discrete informational units. At its core, the universe is not made of matter, but of answers to questions, bits of data that form the foundation of physical law. Wheeler argued that what we call reality grows out of acts of observation, each measurement recording a binary decision in the cosmic ledger. This was not mere metaphor. Quantum theory already hinted that outcomes emerge from probabilities resolved at the moment of interaction, and information became the natural language for describing this process. Physics, once the study of forces and particles, was increasingly reframed as the study of information and its transformations. The universe could be seen not as a machine, but as a system of computation, its phenomena arising from the flow and processing of data. The concept of information soon found a natural home in thermodynamics, the study of energy and entropy. Entropy, traditionally understood as disorder, can also be interpreted as missing information. A container of gas, for example, may be described macroscopically by its pressure and temperature, but to know the exact position and velocity of every molecule would require vastly more information. The entropy is high precisely because that microscopic detail is unknown. In this sense, entropy measures how much information is hidden from us. When Ludwig Boltzmann formulated his statistical understanding of thermodynamics, he laid the groundwork for viewing the arrow of time as a story of information loss. As systems evolve, their accessible information becomes more diffuse, their microstates harder to track. Claude Shannon later formalized information theory, defining information in terms of choices, probabilities, and uncertainty. The parallel between Shannon's definition and Boltzmann's entropy revealed that the second law of thermodynamics, the inevitability of increasing entropy, could be understood as a principle of information dispersal. Heat, randomness, and disorder all point toward a universe where information tends to spread out. In this way, the flow of time itself may be described as the unfolding of information across the cosmos. Nowhere has the marriage of physics and information been more striking than in the study of black holes. These objects, born when massive stars collapse under their own gravity, concentrate matter and energy so tightly that not even light can escape. For decades, black holes were thought of as cosmic prisons, swallowing information forever. But in the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects at the event horizon cause them to emit radiation, slowly evaporating over time. This led to a paradox. If a black hole eventually disappears, what happens to the information that fell inside? According to the laws of quantum mechanics, information cannot be destroyed. Yet black holes seem to erase it. This tension sparked one of the deepest puzzles in theoretical physics. The holographic principle, developed from work by Gerard T. Hooft and Leonard Susskind, offered a resolution. It suggested that all the information contained within a volume of space could be represented on its boundary surface, much like a hologram encodes three-dimensional data on a two-dimensional film. In this view, the universe itself may function holographically, with the information describing everything inside written on a lower-dimensional surface. What appears three-dimensional could in fact be a projection from more fundamental data stored elsewhere. This principle implies that information is not lost in black holes, but preserved on their horizons, woven into the very geometry of space-time. From this perspective, the universe is not only made of information, but also bounded by the limits of how much information it can hold. The maximum density of information in any region is finite, constrained by physical constants. Seth Lloyd, a researcher in quantum computing, once estimated the total computational capacity of the observable universe. According to his calculations, the cosmos could have performed on the order of 10 to the power of 120 operations on 10 to the power of 90 bits since the Big Bang. These are staggering numbers, yet they are finite. The laws of physics act as ceilings on how much data can be processed or stored. Light speed limits the rate of communication. The Planck scale sets the smallest meaningful resolution. Even energy itself can be understood as a measure of information capacity. What emerges is a picture of the universe, not as boundless in its possibilities, but as constrained by its ability to compute. Every physical interaction, from the motion of atoms to the formation of galaxies, may be described as an operation in a cosmic computer. This vision takes the abstract idea of it from bit and anchors it in the measurable capacities of the universe itself. If matter and energy are forms of information, and if spacetime has limits that resemble the properties of computation, then it becomes natural to ask whether the universe itself is structured like a computational bow. Grid. In digital simulations, space is represented as a lattice of points, each storing data that changes according to rules. Something similar may hold true in our cosmos. At the Planck scale, spacetime may be pixelated, with information flowing between adjacent units like updates in a program. The apparent continuity of reality would then be an emergent illusion, just as a video game world appears smooth though it is built from discrete updates on a screen. The holographic principle reinforces this possibility, suggesting that the entirety of three-dimensional reality could be encoded in a lower dimensional structure. Quantum field theory, string theory, and loop quantum gravity all point toward versions of this idea, though from different angles. In each case, what we experience as solid, continuous, and independent may instead be emergent from a deeper informational substrate. This brings the scientific imagination to a threshold. If the universe operates like data, constrained by the laws of computation, and if information is the bedrock upon which reality rests, then the boundary between physics and digital processing grows thin. The next step is to look not only at the cosmos itself, but at the machines we have built. Human computation, from the first algorithms scratched on parchment to the silicon chips of today, may be seen as mirrors of the larger process. As our computers grow in complexity and power, we begin to approach the possibility of simulating aspects of the universe itself. And so the question arises, are our own creations reflecting the true architecture of reality, or are they small echoes within a greater computation we are only beginning to perceive? In the early 20th century, before digital machines filled rooms and later slipped into pockets, the British mathematician Alan Turing imagined the abstract essence of computation. He conceived of a hypothetical device that could read and write symbols on an infinite tape, following simple rules step by step. Though elementary in design, this imaginary Turing machine could, in principle, perform any calculation that could be expressed in logical steps. It was a profound insight. Computation was not about gears or wires, but about processes, rules, and information. With this model, the dream of universal computation was born. Any process governed by logic could be simulated by such a machine. The boundary between mathematics and mechanism dissolved. It meant that reality itself, if governed by laws expressible as algorithms, might one day be reproduced or imitated by artificial means. The seeds of simulating the universe were sown even before the first electronic computers flickered to life. Once physical computers began to appear, their progress was astonishing. In the mid-20th century, early machines filled entire rooms, humming and clattering as they executed thousands of operations per second. Yet within decades, they were shrinking in size and soaring in power. In 1965, Gordon Moore, a co-founder of Intel, observed that the number of transistors on a chip was doubling roughly every 2 years. This observation, later called Moore's Law, became a guiding expectation for the exponential growth of computing. Each generation of machines could perform more operations, store more data, and simulate more complex systems than the last. What began as mechanical calculators evolved into digital powerhouses, capable of modeling phenomena far beyond human intuition. The doubling trend held for decades, driving not only faster computation, but also cheaper and more accessible machines. By the dawn of the 21st century, supercomputers could perform trillions of operations per second, and even consumer devices rivaled the power of the earliest mainframes. This exponential rise gave humanity the tools to begin experimenting with simulations of extraordinary scale and precision. The new power of machines was soon directed toward the natural world itself. Weather forecasting, once limited to educated guesses, became the domain of high-powered simulations that processed atmospheric data on vast grids, updating conditions hour by hour. Proteins, whose folded structures determine the machinery of life, were modeled in silico, allowing scientists to predict shapes and interactions that might never be captured in the laboratory. Entire regions of the cosmos were simulated in digital form, with virtual universes evolving under gravitational equations, star formation models, and dark matter distributions. These computational experiments allowed researchers to explore scenarios impossible to test directly. A climate projection running a century into the future, a protein folding sequence completed in microseconds of computer time, or a galaxy cluster forming across billions of simulated years. All of these became possible because computation could step in where experiment and observation reached their limits. The act of simulation was no longer confined to abstractions. It became a central method of doing science. Each successful model reinforced the sense that reality itself was computationally tractable, that with enough processing power, the workings of nature could be mirrored in code. As computation entered popular culture, its reach extended beyond the laboratory. Video games, once simple diversions with blocks and pixels, grew into vast and immersive virtual worlds. A player walking through a digital landscape experienced an environment governed by rules, rendered in real time by algorithms running on hardware. Characters not controlled by players, so-called non-player characters, followed their own programmed behaviors, creating the illusion of independent existence. Online multiplayer games linked millions of people across continents, all sharing the same digital universe. These experiences were microcosms of simulation, enclosed environments where laws defined behavior, where entire worlds unfolded within the memory of machines. From the outside, there were lines of code, patterns of electrical signals. From within, they felt like coherent spaces with consistent rules. The progression from pixels on a screen to richly detailed landscapes demonstrated how digital processing could create realities that felt increasingly convincing. The difference between virtual and real blurred, not in philosophical speculation, but in lived experience. Each leap in graphical fidelity, artificial intelligence, and world complexity pushed closer to the idea that reality could be simulated wholesale. The trajectory of computing did not stop with classical machines. Quantum computing emerged as a revolutionary new paradigm. Instead of relying on bits that were either 0 or 1, quantum computers used qubits that could exist in superpositions of states. This allowed them to perform certain calculations in ways exponentially faster than classical machines. Problems that would take billions of years for even the fastest supercomputer might, in principle, be solved in days or hours by a sufficiently advanced quantum device. Though still in its infancy, quantum computing promised to simulate quantum systems naturally, since it used the same rules of superposition and entanglement that govern the physical world. For the first time, humanity was building machines that mirrored the strangeness of the universe at its deepest levels. These developments suggested that the line between reality and simulation was thinner than ever. If computation could capture not only the classical mechanics of planets and weather, but also the quantum behavior of atoms and molecules, then the idea of simulating entire worlds no longer seemed fanciful. It became a question of scale, power, and persistence, a matter of when, not if, such simulations might be achieved. Nick Bostrom, a philosopher at the University of Oxford, is best known for crystallizing the simulation hypothesis into a rigorous argument. In 2003, he published a paper that gave structure to a question that had lingered for decades. If computers could one day simulate entire civilizations, what would that mean for our understanding of Tull? Reality itself? Rather than presenting the idea as science fiction, Bostrom treated it as a formal argument about probability, ethics, and the trajectory of technology. His training in philosophy of mind and computational theory gave him a unique vantage point. He could bridge questions of consciousness, the limits of machines, and the mathematics of likelihood. By carefully setting out assumptions and consequences, he reframed the old suspicion, what if we are living in an illusion, into a challenge for rational analysis. At the core of Bostrom's paper was a trilemma, a set of three possibilities that he argued must encompass the truth. The first possibility was that technological civilizations almost always go extinct before developing the capability to create large-scale ancestor simulations. If this were the case, then we need not worry, because such simulations would never exist. The second possibility was that civilizations do develop such power, but they choose not to use it. Perhaps ethical considerations prevent them, or perhaps the resources required are judged not worth the effort. The third possibility was that civilizations do survive and do choose to run vast numbers of simulations of their ancestors, whether for science, entertainment, or reasons beyond our comprehension. If the third is true, then the number of simulated beings would vastly outnumber the beings in base reality. Since any conscious entity has no privileged position by which to determine whether it is simulated or not, the probability would then tilt strongly toward us being simulated. Bostrom presented these three possibilities not as speculation but as a logical structure. At least one must be correct. The unsettling part of the argument came in the probabilistic reasoning. If civilizations reach the point of running simulations, and if they run many of them, then the number of conscious beings living inside simulations would quickly dwarf the number living outside. Imagine one advanced society running millions of detailed historical simulations, each populated by billions of conscious agents. The inhabitants of base reality would then represent only a tiny fraction of the total number of minds in existence. From the standpoint of probability, any randomly selected conscious experience would almost certainly be inside a simulation, not outside. The odds of being in base reality would be vanishingly small. The only way to avoid this conclusion would be if either civilizations never reached such power, or they almost never chose to exercise it. Bostrom argued that since we cannot rule out the technological feasibility of such simulations, and since we cannot know the intentions of future civilizations, we must accept that one of these three branches must hold. It was a stark application of statistical reasoning to the very question of existence. If the third branch is true, and we are living in a simulation, the implications are profound. Ethics takes on new layers. Do the creators of such simulations bear moral responsibility for the lives within them? If we are conscious and capable of suffering, then our experiences would seem as morally significant as those of base reality beings. Does this mean an advanced civilization might be running countless simulated lives, each filled with joy and pain, purely for research or entertainment. The question extends to free will. If our thoughts are the product of computational processes in a greater machine, are we truly autonomous, or are we constrained by the architecture of the simulation? There are also questions of meaning. If the universe is simulated, does that diminish its significance, or does it elevate it as part of a larger structure? Religious and metaphysical interpretations arise naturally. Some liken the creators of such simulations to gods, possessing power over the laws of nature. Others suggest that simulated beings, if they become self-aware, might themselves create simulations, producing a nested hierarchy of realities within realities. The concept destabilizes traditional boundaries between real and artificial, natural and constructed. At a personal level, the simulation argument can be unsettling or liberating. If reality is simulated, then many of the constants we take for granted, laws of physics, limits of space, might be adjustable parameters, like settings in a program. The fragility of our existence becomes more apparent, as the simulation could, in theory, be altered or terminated at any moment. Yet at the same time, meaning may not be diminished. Our joys, our sorrows, our struggles remain real to us, regardless of the substrate on which they run. To live in a simulated world does not erase the reality of lived experience. The recognition, instead, invites humility and wonder. Whether or not we are simulated, the universe remains astonishingly rich, filled with mystery and complexity. Bostrom's trilemma reframed the debate. Instead of asking whether we are in a simulation, it asked which branch of the trilemma we occupy. If the first is true, then civilizations tend to destroy themselves before reaching technological maturity. If the second, then civilizations survive but refrain from running simulations. If the third, then we are almost certainly in one. The unsettling weight of probability made the argument difficult to dismiss. Still, Bostrom himself emphasized that the argument was not proof, but a structure of reasoning. It invited us to confront the assumptions of our own existence and the trajectories of our technology. The next question is whether such an argument can ever move beyond philosophy into science. Can the hypothesis be tested, or is it forever beyond empirical reach? This is where physicists and cosmologists have stepped in, proposing possible signs that might distinguish base reality from simulation. The journey turns from philosophy to physics, from speculation to attempts at measurement. The question becomes, if we are living in a simulation, what clues might the universe leave behind? If the simulation hypothesis is more than philosophy, then it should leave fingerprints on the world we can measure. Scientists have therefore wondered whether the universe itself might bear marks of an artificial structure beneath its apparent smoothness. One idea focuses on cosmic rays, high-energy particles that streak across the cosmos and strike Earth's atmosphere. If space and time are continuous, these rays should arrive from all directions with no preferred pattern. But if reality is built on a lattice, like a grid of pixels, then there might be subtle anisotropies in the way these particles distribute themselves. The grid could act as a cosmic scaffold, influencing how particles move at extreme energies. Researchers have explored this by looking for small deviations in the arrival directions of the highest energy cosmic rays. If a preferred alignment were found, it might suggest that spacetime itself is not perfectly continuous, but has an underlying discreteness. Such an observation would be the kind of evidence simulation theorists imagine, a sign that the fabric of the universe is not seamless but patterned, much as a digital image reveals its pixels under sufficient Cree. Magnification. The search for pixelation does not stop with cosmic rays. Particle accelerators, such as the Large Hadron Collider, probe nature at energies that approximate the smallest scales known. Here, scientists look for hints that spacetime itself may be quantized. If the universe has a smallest unit of length or time, then high-energy particles might scatter in ways that reveal this granularity. Just as the smooth curve of a circle drawn on a low-resolution screen betrays its jagged edges when enlarged, spacetime may reveal itself as blocky under enough magnification. Efforts to detect such effects are challenging because the scales involved are unimaginably tiny. The Planck length is many orders of magnitude smaller than anything current technology can probe directly. Still, theorists suggest that certain patterns, such as limits in the spectrum of high-energy gamma rays or anomalies in the propagation of light across vast cosmic distances, might act as indirect hints. If light traveling billions of years arrives slightly distorted in ways that cannot be explained by known physics, it could be a sign that the path it traveled was laid across a discrete grid rather than a continuous expanse. These experiments represent some of the boldest attempts to test whether reality itself is digital at its foundation. Beyond the search for granularity, physicists consider the energy requirements of a simulated universe. Every computation requires resources. A simulation capable of sustaining billions of conscious beings, along with the complexity of galaxies, atoms, and quantum fluctuations, would require vast computational capacity. Some researchers argue that the observable universe already appears to run close to such limits. The maximum number of operations that could have been performed since the Big Bang, given the energy and time available, has been estimated at around 10 to the power of 120. That is a colossal figure, yet still finite. If our universe is indeed a simulation, it may be constrained by these same ceilings. Certain physical limits, such as the speed of light or the conservation of energy, might reflect not arbitrary laws, but the resource boundaries of the computational substrate. The very fact that nothing can exceed the speed of light, no signal outrun causality, may be akin to a frame rate cap or a processing limit in a cosmic program. In this interpretation, physics is not merely descriptive, but prescriptive, defining the operational constraints of the machine we inhabit. Another line of speculation concerns the constants of nature. Why is the speed of light exactly what it is? Why do the fundamental charges, masses, and coupling strengths of particles take the values we measure? These numbers appear arbitrary, yet they are precisely tuned to allow for the existence of stars, chemistry, and life. Some physicists propose that these constants are not fundamental at all, but could be settings in an underlying code. Change them slightly, and universes become sterile, with no stable matter or no possibility for complexity. In the simulation hypothesis, such tuning might be no mystery at all. It could simply reflect choices made by the simulators. Just as a programmer sets parameters for a virtual environment, adjusting gravity or light intensity, so too might the creators of our world have adjusted the constants to produce a cosmos capable of K, evolving in interesting ways. This perspective offers a radical reframing of fine-tuning arguments. Instead of invoking chance or multiverse explanations, it suggests intentional design within a computational architecture. For those who consider the possibility, it implies that what we call the laws of physics may in fact be configurable features, choices rather than necessities. Yet every attempt to find evidence for simulation must contend with deep critiques. The most significant is that the hypothesis may not be falsifiable. If we detect no signs of discreteness or anomalies, simulation proponents can always respond that the simulation is simply detailed enough to hide its scaffolding. If we do find anomalies, skeptics can counter that they may just reveal new physics within base reality, not proof of simulation. In this way, the hypothesis risks being insulated from disproof, making it more philosophy than science. Another challenge is that even if the universe exhibits limits resembling computational constraints, that does not necessarily imply simulation. It may simply mean that information and computation are natural descriptions of how reality operates at its deepest levels. The line between a computational universe and a simulated one is subtle, and critics argue that it may never be possible to distinguish the two. Philosophers caution against treating metaphor as evidence, warning that the language of pixels and programs may be helpful but not definitive. The danger is to mistake the map for the territory, confusing useful analogies with literal truths. Still, the search continues. For many researchers, the allure of the question lies not in its definitive answer, but in the way it stretches the imagination and reshapes scientific inquiry. Looking for signs of simulation invites us to probe the limits of physics, to test the structure of spacetime, and to confront the deepest questions about why the universe is the way it is. Whether the anomalies found are signs of hidden scaffolding or simply new physics, the exploration advances our understanding. And if we are simulated, then the next question naturally follows. Who would build such a world, and for what purpose? The mystery does not end with evidence, it extends to the very nature of the creators who might stand beyond the boundaries of our reality. Artificial intelligence is often thought of as a tool for solving problems, predicting patterns, or automating tasks. Yet one of its most profound powers lies in its ability to create worlds. Already, AI systems are used to generate models of weather, ecosystems, and the spread of diseases. They do not merely calculate outcomes, but simulate environments where variables interact dynamically. In these digital arenas, agents can act, react, and adapt, producing emergent behavior that was never explicitly programmed. In this sense, AI is a world builder, taking sets of rules and running them forward to see what landscapes emerge. Each simulation becomes a miniature cosmos governed by mathematics. With growing sophistication, these artificial worlds become more detailed, responsive, and complex. What once required human-crafted equations can now be produced by systems that learn patterns directly from data. The boundaries between modeling, simulating, and inventing blur. An AI-driven model is no longer just an abstraction. It is an evolving environment with its own laws, behaviors, and outcomes. This trend suggests a future where the creation of simulated realities may not be done solely by human programmers, but by AI systems constructing and refining worlds of their own design. Generative neural networks exemplify this shift. These systems are trained on massive datasets, learning patterns and correlations that allow them to produce entirely new content. In text, they generate coherent passages of language. In images, they create pictures of people, places, and objects that never existed. In audio, they compose music or synthesize voices indistinguishable from recordings of real individuals. Each of these outputs is not a simple copy, but a new creation born from learned structures. When extended to dynamic systems, such networks can produce environments that evolve over time, filled with agents whose behaviors are shaped by patterns extracted from reality. Synthetic data generated this way already fuels training for other AI systems, standing in for real-world experience. But the implications reach further. If AI can construct data that imitates reality with fidelity, then it can also create alternative realities with their own consistent rules. A generative model trained on the physics of fluids can invent new simulations of oceans and rivers. One trained on astronomical data can create entire galaxies, consistent in detail, yet unique in form. These creations resemble new worlds, not only visually but structurally. The more advanced the generative process becomes, the more these worlds begin to look less like imitations and more like independent realities within a machine. The role of game engines amplifies this trend. Originally designed to render graphics and manage interactions in video games, these engines have become versatile platforms for simulating worlds of astonishing complexity. Within them, terrain is generated, physics simulated, weather modeled, and agents animated, all according to consistent sets of rules. To a player, these environments feel like places, complete with landscapes, climates, and societies. To a developer, they are systems of code, variables, and algorithms working in concert. As engines grow in sophistication, they allow for procedural generation, where entire worlds are created on the fly by algorithms rather than handcrafted design. Mountains, forests, and cities spring into existence according to rules, producing worlds that are both coherent and endless. With enough processing power, these virtual environments can expand to planetary scales with no fixed boundaries. Combined with advances in AI, the agents populating these worlds can now act in more realistic, adaptive ways, making the environments feel alive. What emerges are microcosms of reality itself, digital universes with their own physical laws, agents with agency, and histories that unfold uniquely with each run. They are, in effect, self-contained realities within machines. At the heart of these realities are non-player characters, or NPC, the agents that inhabit virtual worlds alongside human participants. Traditionally, NPCs followed simple scripts. They repeated lines, walked set paths, or offered limited interactions. But with AI integration, they have begun to exhibit behaviors that appear spontaneous, adaptive, and lifelike. An NPC in a modern simulation might learn from its environment, react to unexpected events, or even develop strategies in ways the programmers did not anticipate. This raises the question of where the line lies between scripted behavior and genuine agency. If an NPC adapts, learns, and changes in ways that surprise even its creators, does it begin to resemble a conscious agent? Consciousness is more than behavior, yet from the inside, our own awareness is expressed through behavior, reaction, and learning. If enough complexity and autonomy are given to digital agents, the difference between simulation and life narrows. Philosophers and cognitive scientists have debated whether consciousness might emerge in sufficiently complex systems, regardless of their substrate. If this is true, then NPCs of the future may not just appear lifelike, but may, in some sense, become alive. The ethical implications are vast. To simulate millions of agents capable of suffering or joy would be to create entire societies of digital beings whose experiences matter. In that case, running a simulation would not be trivial entertainment, but the creation of worlds filled with genuine lives. This question leads directly to the notion of substrate independence. If consciousness is the product of patterns of information processing, then it may not matter whether those patterns are implemented in neurons, silicon, or something else entirely. The brain is a biological computer, processing signals, integrating information, and generating experience. If the functional organization is what counts, then consciousness could, in principle, be instantiated in any medium capable of supporting the same complexity. This is the foundation of the idea that minds might one day be uploaded into machines, or that artificial beings could achieve awareness. Within the simulation hypothesis, it suggests that our own consciousness might already be implemented, not in neurons of flesh, but in circuits of some higher machine. If the substrate does not matter, then reality itself may be indifferent to what it is built from. What matters is the structure of the processing, the flow of information, the integration of patterns. Under this view, simulated beings are not merely imitations of life, they are life, as real as any biological organism, because the substrate is irrelevant to the existence of experience. And yet, as we explore these possibilities, we are reminded to compare them to ourselves. Our own consciousness, arising from the wet networks of the brain, remains only partly understood. We are the only example we know of minds that reflect upon themselves, that imagine the possibility of simulation, that create worlds within worlds. As we peer into the capacities of AI to simulate, generate, and invent, we are in fact holding up a mirror to our own nature. Whether machines will one day host experiences as vivid as ours is still uncertain. But the very fact that we can contemplate such a future hints at a strange symmetry. If we can create worlds filled with agents that wonder about their reality, then perhaps our own wondering is evidence of a larger world beyond ours, one in which we too are simulated agents peering upward into the subtler unknown. Consciousness has long been one of the deepest mysteries in philosophy and science. We can describe the motion of planets, the behavior of atoms, and the evolution of galaxies. But the simple fact of being aware the feeling of having an inner life remains elusive. This is often called the hard problem of consciousness. While neuroscience can trace neural circuits, measure brain activity, and correlate it with mental states, there is still a gap between the physical processes and the subjective experience they produce. No scientific theory fully explains why patterns of electrical signals inside a brain should give rise to the vivid texture of thought, sensation, and self-awareness. Why should certain arrangements of neurons firing lead to the redness of a sunset, the ache of a memory, or the flow of inner dialogue? This gap raises a profound question. Is consciousness fundamental, irreducible to physical description, or is it emergent, arising naturally when matter is organized in a certain way? Within the context of simulation theory, the answer matters greatly. If consciousness depends on something beyond information processing, then it may be bound to biological organisms. If it emerges from complexity alone, then it could just as easily exist within a simulation. One clue comes from the study of perception. Our brains do not passively record the outside world. Instead, they actively construct an internal model of reality. Sensory information streaming in through eyes, ears, and skin is noisy, incomplete, and ambiguous. The brain integrates these signals with prior expectations to generate a coherent picture of the world. Neuroscientists increasingly describe perception as a predictive process, where the brain continuously forecasts what should be happening and corrects those predictions with incoming evidence. This predictive coding framework means that much of what we perceive is not raw data, but inference, a best guess that keeps us oriented and functional. The experience of reality is therefore already a kind of simulation, a model maintained inside the skull. We do not see photons, we see interpretations. We do not hear vibrations, we hear patterns our brains assign to voices or music. This construction is seamless most of the time, but it reveals itself when errors occur, when a shadow looks like a figure, when a sound is misheard, when we dream and the brain generates an entire world without any external beat. Input. Consciousness, in this view, is bound up with the brain's internal simulations of reality. The ease with which perception can be tricked underscores how fragile and constructed our sense of reality is. Optical illusions demonstrate that the brain can be led to see movement where there is none, colors that shift with context, or lines that appear bent though they are straight. Auditory illusions cause us to hear words in random noise or tones that rise endlessly in pitch. Neuroscience experiments reveal how malleable the sense of self can be. In the rubber hand illusion, for instance, a subject comes to feel that a fake hand is their own when it is stroked in synchrony with their hidden real hand. Virtual reality systems amplify these effects, creating convincing sensations of presence in environments that do not exist physically. Dreams push the point further still. Every night, our minds conjure immersive realities populated by people, places, and events. complete with sensory richness and emotional weight, that we accept them as real until waking suggests just how easily consciousness can inhabit a world that is not there. All of this supports the idea that reality, as experienced, is always mediated, always interpreted. The brain is a simulator, and we live within its model of the world. If consciousness is indeed the product of complex information processing, then there seems no reason in principle why it could not exist in a simulation. The brain processes inputs, integrates information, and produces subjective experience. If another system, say, a computational architecture designed with sufficient complexity, could perform the same functions, then consciousness might arise there as well. This is the essence of the argument for substrate independence. Minds are not tied to biology. They are tied to organization and function. If neurons can give rise to awareness, so too might transistors, optical circuits, or quantum states, provided the structure supports the right patterns of integration. This is what gives the simulation hypothesis its force. If our reality is informational, and if information processing can produce consciousness, then there is no barrier to beings within a simulation being just as aware, reflective, and real as beings in base reality. From the inside, the experience would be indistinguishable. To dream, to love, to suffer, to wonder, these could all be genuine within a computational universe. Our sense of self would not reveal whether we are biological or simulated. Consciousness, being emergent, would be equally authentic in either case. Still, not everyone agrees that consciousness can be reduced to information processing. Some scientists argue that biology provides essential qualities that no machine could replicate. Neurons are not simple switches, but highly complex, chemically active cells, operating with layers of dynamics far beyond digital logic. The brain is also embedded in a body that senses, moves, and acts in the world. This embodiment, some claim, is essential to experience. Without a body, without hormones, without physical feedback, a computational model might replicate behavior but never produce the lived richness of awareness. Others suggest that consciousness is fundamental, not emergent, and cannot be simulated in principle. From this perspective, a simulated agent may appear intelligent, but would be an empty shell, lacking true subjective experience. This counterargument holds that while AI and simulations may approximate intelligence, they do not produce the inner spark of awareness that defines being. If so, then consciousness remains tied to biology, and the beings of a simulation would be illusions, not minds. Yet whether consciousness is emergent or fundamental, simulated or biological, the questions it raises inevitably spill into culture and imagination. From philosophy to science fiction, we see the reflection of our struggle to define what is real, what is alive, and what it means to be aware. The debate does not close with neuroscience or physics, but opens into the stories we tell, the fears we express, and the hopes we project. It is here that simulation theory becomes not just a scientific speculation, but a cultural mirror, revealing the anxieties and aspirations of an age in which machines and minds seem ever more entwined. Writers have long wondered whether reality is less than it seems. Long before simulation theory was formulated in academic language, authors and visionaries imagined universes that might be fabricated, deceptive, or layered. Philip K. Dick, the American science fiction writer, returned to this theme repeatedly. In his stories, characters questioned their memories, doubted their senses, and discovered that the worlds around them were not what they appeared to be. In novels such as Ubik and Time Out of Joint, reality is shown as fragile, subject to sudden collapses or distortions. Dick was not alone. Earlier thinkers like Jorge Luis Borges had explored labyrinths, mirrors, and infinite libraries, each a metaphor for realities within realities. These early voices treated illusion not merely as a literary device, but as a profound philosophical possibility. If perception can be untrustworthy, if memory can be altered, then what grounds do we have to say with certainty what is real? Such stories resonated because they echoed the doubts that accompany human consciousness itself. We live within a constructed perception, and the suspicion that this construction might extend to the universe at large is both unsettling and compelling. The cultural turning point came in the late 1990s with The Matrix. The film introduced a wide audience to the possibility that reality itself might be a vast computer simulation. Its imagery, humans asleep in pods, their minds fed with artificial experiences, captured the idea in unforgettable form. More than a spectacle of action and special effects, the story posed a philosophical dilemma. If the world feels real, tastes real, and behaves according to consistent rules, how could anyone know it was false? The film drew from philosophical traditions ranging from Plato's allegory of the cave to Descartes' demon of deception, but it translated those ideas into a digital age. Audiences left theaters asking themselves whether their own lives might be illusions. The cultural impact was enormous. Red pill and blue pill became shorthand for awakening to hidden truths. The film's influence reached not only popular culture, but also academia, where the simulation hypothesis began to be discussed with greater seriousness. By dramatizing the concept with clarity and immediacy, The Matrix ensured that simulation theory would remain part of public imagination. Other cultural portrayals expanded on the theme, each adding new dimensions to the idea of illusory worlds. Christopher Nolan's Inception imagined nested layers of dream realities, where characters could descend multiple levels deep into fabricated landscapes. The tension came not from whether the dream worlds felt convincing they did, but from whether one could reliably distinguish them from waking life. The film's ending, with its ambiguous spinning top, left audiences questioning whether the protagonist ever escaped illusion. In another direction, Tron explored what it might mean to be pulled inside a digital system. My programs became characters, and landscapes were composed of code. The sleek, visual style made tangible the notion of living inside computation. Later, Westworld revisited the theme through artificial beings inhabiting simulated realities of their own, raising questions not only about what is real, but about what counts as conscious, alive, or deserving of rights. Each of these cultural works did more than entertain. They served as laboratories of imagination, allowing audiences to test the boundaries of reality and illusion in ways that science alone could not. The emotional weight of these stories, fear, awe, empathy gave the abstract problem of simulation theory a visceral immediacy. Culture does not merely reflect scientific speculation, it also inspires it. When scientists and philosophers explore the possibility of simulation, they often reference works of art and literature as much as equations. The interplay runs in both directions. Cultural depictions shape public interest, which in turn influences funding, research agendas, and the willingness of academics to tackle unconventional ideas. The notion of virtual reality, for instance, moved from speculative fiction into engineering laboratories and is now an active field of development. Similarly, thought experiments inspired by films or novels can help scientists sharpen their concepts. What would it mean for information to be indistinguishable from reality? How could one detect the limits of a simulated environment? These questions are easier to explore when dramatized in narrative form. By putting human characters inside illusions, stories give scientists a way to consider the practical, ethical, and experiential consequences of the theory. Culture thus acts as both a testing ground and a bridge, turning abstract hypotheses into lived experience. In this way, the collective imagination helps drive the frontiers of inquiry. And yet, cultural portrayals also sharpen skepticism. For every story that makes simulated worlds seem plausible, there is an equal reminder of how compelling illusions can be without being real. The fact that our imaginations so readily generate these scenarios might say more about human psychology than about the nature of the universe. Just because we can picture living in a simulated world does not prove that we do. Skeptics note that films and novels can dramatize any concept, from time travel to magic, without those concepts being true. Simulation theory must stand or fall on scientific and philosophical grounds, not on narrative appeal. Thus, after surveying culture's vast engagement with the theme, we return to the need for critical examination. How strong is the evidence? What are the arguments for and against? To move beyond stories and into science, we must now weigh the case for skepticism. One of the most direct criticisms of the simulation hypothesis is also one of the simplest. It may be harder to simulate a universe than to create one. Proponents of the theory often assume that an advanced civilization, having mastered computation, would be able to generate countless virtual worlds, each populated by conscious beings. But consider the sheer scope of such a task. To reproduce a universe down to every atom, every quantum state, every interaction across billions of light years would demand resources beyond comprehension. A simulation detailed enough to be indistinguishable from reality may require as much energy and information as the universe itself contains. In that sense, simulating a universe is no shortcut. It may be just as demanding as making one. Some argue that a simulation could be more economical, perhaps only modeling the parts of reality that observers directly interact with. But even this strategy raises complications. Conscious beings are not predictable scripts they probe, test, and observe. Any shortcut risks detection. The argument from complexity suggests that the project may not be feasible, even for civilizations far beyond our own. Rather than being easy or inevitable, universe-scale simulations may be practically impossible. Closely related to this is the problem of computational limits. Physics itself imposes boundaries on how much information can be stored, processed, and transmitted in a finite region of space. According to Landau's principle, every bit of information processed requires a minimum amount of energy. The Bekenstein bound suggests there is a maximum density of information that can be packed into a finite space before it collapses into a black hole. Light speed sets ultimate limits on how quickly information can travel. Even if an advanced species had unimaginably powerful computers, they would still be constrained by these physical laws. A simulation that attempted to model every particle in a universe, or every detail of every conscious mind, would face bottlenecks in energy and storage. Proponents sometimes suggest that such civilizations could access new forms of physics, perhaps exploiting quantum computation or higher dimensional resources. But unless the basic principles we know are radically transcended, the limits remain daunting. A universe like ours, rich with fine structure and governed by delicate laws, may simply be too vast and intricate to reproduce in silico. The hypothesis presumes not only extraordinary advancement, but also a violation of known computational boundaries. Beyond technical feasibility, philosophical counterarguments strike at the logical foundation of the hypothesis. One major issue is unfalsifiability. If every observation within a simulation is itself generated by the simulation, then no observation can prove or disprove the theory. Any apparent evidence of the base reality could itself be simulated. This makes the hypothesis difficult, perhaps impossible, to test. Scientific theories typically gain strength by being open to falsification, by making predictions that could, in principle, be shown wrong. The simulation argument, in its most general form, seems to evade this standard. Another philosophical concern is epistemic caution. Human beings have a long history of projecting metaphors of the age onto the cosmos. In the mechanical revolution, the universe was compared to a clockwork. In the industrial age, it was likened to a machine. In the digital era, we naturally imagine it as computation. Skeptics warn that this may simply be another projection, reflecting cultural context rather than objective truth. Just as the universe is not literally a clock, it may not literally be code. Without clear evidence, the simulation hypothesis risks being more a mirror of human imagination than a description of reality. There are also alternative explanations for why reality feels strange without resorting to the idea of simulation. Quantum mechanics, with its uncertainty and entanglement, can seem alien and counterintuitive, but this does not require that the universe is artificial. It may simply mean that reality operates according to rules beyond classical intuition. Similarly, the pixel-like limits suggested by the Planck scale do not imply computation. They may reflect the fundamental discreteness of spacetime, independent of any designer. The fine-tuning of physical constants, often cited as evidence of design, may also have natural explanations, such as multiverse theories in which many universes exist with different parameters, and we simply inhabit one compatible with life. Even the malleability of perception and consciousness, so often invoked to suggest illusion, can be understood as evolutionary adaptations of brains built to survive, not as evidence of simulation. In short, the strangeness of reality may be entirely natural. The fact that physics defies intuition, or that consciousness is difficult to explain, does not necessarily point to digital origins. It may only reflect the limits of human understanding at this moment in history. These critiques do not eliminate the allure of the simulation hypothesis, but they remind us to weigh its scientific and philosophical status carefully. Enthusiasm must be balanced with skepticism and cultural imagination distinguished from testable theory. Yet even as doubts accumulate, the conversation shifts toward a different frontier: the consequences of taking the idea seriously. If simulations were possible, what risks would follow? Could advanced beings shut us down at will? Would creating simulated minds impose moral responsibilities? And if reality is indeed computation, what future lies ahead for humanity as it builds ever more powerful simulations of its own? To explore these questions, we move from criticism to consideration of existential risk and the perspectives that shape our future. If reality is a simulation, then it carries with it a new kind of fragility. For in addition to the natural risks we already face, asteroid impacts, supernovae, climate change, pandemics, there exists the possibility that the simulation itself could be ended by its creators. This is not a fear of cosmic accident, but of deliberate or indifferent termination. If the beings who run the simulation lose interest, turn off their machines, or redirect their resources, then our universe would vanish without warning. From within the simulation, there would be no sign, no cosmic tremor, only the sudden erasure of everything. Some philosophers speculate that catastrophic events within history, unexplained shifts in probability, or apparent fine-tuning, might be artifacts of system adjustments. More sober voices caution that this is speculation stacked upon speculation. Yet the idea persists because it makes plain the existential risk unique to a simulated reality. We are not only vulnerable to natural disasters, but also to the choices of beings outside our comprehension. This recognition adds a peculiar layer of humility. It suggests that, in the grandest sense, survival may not be entirely in our hands. Even if we never know for sure whether our world is simulated, ethical questions about creating simulations remain pressing. As our own computational power grows, the possibility of simulating conscious beings becomes more than a thought experiment. Should we do it? If minds within simulations are capable of suffering or joy, then running them carelessly would be a profound moral failure. Nick Bostrom and others have argued that if we accept simulated minds as real, then we already live in a moral universe of staggering responsibility. Each simulated world would contain entire civilizations of individuals deserving consideration. To switch them off casually would be indistinguishable from mass extinction. Yet others argue that simulations could be designed without true consciousness, that what appears to be a mind might be only a behavioral imitation. The difficulty is that we lack a clear test for consciousness, even among ourselves. To imagine building whole worlds filled with beings whose inner lives we cannot confirm is to face one of the deepest ethical dilemmas of the future. Should we refrain entirely or proceed with caution, knowing that our actions might echo across layers of reality? Technology continues to push us closer to these dilemmas. Virtual reality today is still crude compared to the fidelity of waking life, but it grows more convincing each year. Headsets track motion, generate three-dimensional soundscapes, and render environments that respond instantly to user actions. Artificial intelligence populates these worlds with agents that appear responsive and adaptive. The path from immersive games to simulated societies is not far-fetched. Given enough time, virtual realities could approach the point of being indistinguishable from the physical world. Advances in brain-computer interfaces hint at even deeper integration, bypassing screens altogether and feeding signals directly into neural pathways. Quantum computing, if developed at scale, could provide the raw power needed to simulate physical laws at extraordinary detail. Each of these technologies is still young, but their trajectories point toward the possibility of constructing digital realities of unprecedented complexity. If such worlds become possible, the line between entertainment, research, and new forms of existence will blur. What begins as simulation for play or science could become the foundation of entire societies within machines. Amid these possibilities, questions of meaning rise to the surface. If we are in a simulation, does that diminish or enhance the significance of our lives? For some, the idea is unsettling, reducing existence to a kind of experiment or fiction. For others, it is liberating, suggesting that even if the universe is artificial, our experiences remain genuine to us. Pain, joy, love, curiosity all retain their force, whether they occur in base reality or within a simulation. Indeed, if consciousness is the ground of experience, then meaning resides within it, not in the substrate that hosts it. Our choices, our bonds, and our aspirations retain weight, regardless of whether they unfold in silicon or in spacetime. In this view, the possibility of simulation does not erase human purpose, but reframes it. Life is meaningful not because of where it occurs, but because it is lived. Whether we are the first reality or one of many layers, the significance of our existence flows from within. To grapple with the simulation hypothesis is to reflect on meaning itself, and to recognize that perhaps meaning has always been independent of external guarantees. And so the inquiry turns from speculation to reflection. The simulation hypothesis invites us to imagine risks, responsibilities, and futures beyond our current reach. It confronts us with the fragility of existence and the vastness of possibility. Yet at the same time, it returns us to the present, to the lived reality we inhabit. Whether real or simulated, this moment, this consciousness, this fragile universe of experience is ours to cherish. As we close the circle of argument and return to reflection, we prepare to drift from science back into wonder, and from wonder into rest. The night has carried us far. We began with the question of whether reality is solid and knowable, or fragile and elusive, and followed its echoes through physics, philosophy, and imagination. We lingered with quantum uncertainty, traced the hints of digital structure, and explored the daring thought that our world might be a simulation. We listened to skepticism, to the weight of complexity, and to the possibilities of future technologies. Each step opened new doorways, yet none closed the mystery. And perhaps that is the quiet gift of such a journey. To realize that even if the universe were woven from data, even if every particle and every thought were coded within some deeper architecture, the meaning of our lives would remain untouched. The joy of a moment, the comfort of a voice, the warmth of memory and connection, these do not vanish because of what lies beneath them. They belong to us as lived experience. Whether the universe is made of equations, pixels, or something stranger still, the experience of being alive is always its own truth. So now, as the questions fade into silence, allow yourself to drift into rest. Feel the steady rhythm of your breathing, the slow quieting of thought. The mysteries will wait for you. The cosmos, simulated or not, will keep turning while you sleep. For tonight, you need only let go. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.